Okay, for this test, next test, there's gonna be a lot of structures. So you can have a 3x5 card, both sides. And you can write as tiny as you can. If you all have young eyes, should not be a problem. The way I would suggest doing it is do your landscape in Word, then use the Word to reduce it down. That way, you get smaller type that's really legible. And you can have, if you want to do it that way, shrink it down, and then you can have two one sides for your 3x5 card. Or you can have it, cut it out and keep them together with. Okay. All right. Any questions about things? Okay. It takes me a while to grade these tests. This looks like it's like the pages long. It's fine. Okay, 5 times 64. So it just takes a while. Organic tests are longer because of the structures, etc. Okay, so let's continue on with sugars. Now, this cyclization that we went through Monday is extremely important. Why it's important is number one, when it opens up, it exposes an aldehyde or one of the ketones that are also susceptible to oxidation. It opens, closes, opens, closes. The more cyclic it is, the more stable it is. But it's just the bottom line, it opens up. Now, this is a hexose, a 6-sided heterocyclic sugar. The 5-sided ones do the same thing, like fructose, for example. Now, a couple things. When this opens up and then closes back down, the anomeric carbon hydroxyl group can be either up or down. So you have two versions of glucose, an alpha and a beta. Beta goes up, alpha goes down. So when you specify the glucose, you have to specify whether it's a beta or an alpha version. You don't have to say D, because we're only working with D forms of the carbs, and no L's at all. But you do have to specify if there's a hemiacetal present. You have to specify whether it is alpha or beta. Okay, so in general, if you have a 6-sided heterocyclic carbohydrate, the ring is called a pyranose ring. Pyranose. Heterocyclic meaning the elements of the cyclic atom are not all carbon. So in carbohydrates, you always have an oxygen stuck in there. That's the heterocyclic part. A furanose ring is a 5-membered ring. Now they all have, the common ones, they all have 6 carbons. It's just that they're not in the ring necessarily. Okay, there's yet another term for isomers. Anomers. Anomers differ in which way the anomeric carbon is located? Now, when fructose opens up and closes, it exhibits not an aldehyde, but a ketone. But the ketone is one of the exceptions for oxidation. So there are three versions of ketones that can be oxidized. When fructose opens up, it includes one of them that can be oxidized. So fructose can be oxidized, even though it opens up to a ketone. And it's got alpha, beta forms of it again. So notice in the anomeric carbon, there's one OH that's directly connected to it, and there's another OH one away. This one, not the one that's alpha beta. Only the one attached to the anomeric carbon can be alpha beta. So it opens up to this here, and this is the ketone. Oh, I already have an arrow there. But this is the anomeric carbon here. The thing shifted over in its place. So when this opens up, it opens up from hemiketal, not a hemiacetal, because it opens up to a ketone. Numbering on glucose are 6-membered rings, 5-membered rings. The numbering for 5-membered rings, the anomeric carbon is carbon number 2. On 6-membered rings, anomeric carbon is number 1. Okay, all right. Now, I mentioned this before about this reducing sugar. A reducing sugar can be oxidized because when it opens up, it ends up opening up to an aldehyde or one of those special ketones, which are readily oxidized. If that's the case, then that's a reducing sugar. The only time it'll open up if it's a hemiacetal. So somewhere on the molecule, say it's a polysaccharide, that means we have monosaccharides all over the place, one and one. If one of them has a hemiacetal in it, it's a reducing sugar. So that's the key look for on this reducing sugar. Look for hemiacetal. So if hemiacetal is present, boom, it can be oxidized because it opens up to an aldehyde. Now, when you do your carbohydrate unit or a wet lab, you're going to be using a number of different tests. Test whether it's a reducing sugar, a not a reducing sugar, is it a furanose ring, pyranose ring, that kind of stuff. One of the popular tests is a Benedict's test. And what that does, it oxidizes copper to copper 1 because aldehyde's present. Now, because the Benedict solution starts off with the copper plus 2 ion, it's very blue. When it's reduced, it turns out to be copper 1, and it's not blue at all. It's either orange or kind of a greenish color, and it happens very fast. You're going to find when you put it in the boiling water bath, it turns like in 2 or 3 seconds. It'll go boom. So some of the tests you're going to be doing takes a while, a couple minutes, 3 minutes. Tollens test, for example, using silver, takes a while, but Benedict's is really fast, really good tests. Okay, so let's look at glucose going through Benedict's tests. Okay, you're going to starting off with beta glucose, but it could be galactose or whatever. And I'm going to draw it in the cyclic form first. Then I'm going to open it up to expose the aldehyde. Now, if we put in the Benedict solution, copper plus 2, in a alkaline environment, what's going to happen is this guy gets oxidized. That means something's got to be reduced. Oxidation cannot happen unless reduction happens as well. No exceptions. Okay, so what's going to happen? Now remember, there's an H here. And oxidation in organic chemistry, we're going to lose a hydrogen. All right, so that's what's going to be oxidized, that loss of the hydrogen there. So we're going to redraw this. So normally an aldehyde is oxidized to an acid, but in an alkaline environment, the hydrogen's lost to water. So you're left with the acid salt. Okay, so that's oxidation. This is reduction. Now, normally the copper 1 is tied up with an oxygen, which is that rusty color. Okay, so absolutely you need to remember this reaction. You will see it at least twice on the test, at least twice. Now, what I did for your dry lab for unit 2, I gave you a bunch of carbohydrates, and then I answered 5 or 6 questions about each one of them. And look at the answer. That's going to be very similar to your tests. So you need to determine, is this carbohydrate a reducing sugar? If yes, write the reaction. If no, why not? You have to name the carbohydrate. You should be able to name, where the anomeric carbons are as well. And this includes monosaccharides, disaccharides, oligosaccharides, and polysaccharides. Okay, is this reaction straightforward? Okay, the problem with this reaction, the structures. Yeah,
I was just wondering when this test,
when what?
when the next test.
If you look under lab lecture schedule, you'll see it. And if you remind me towards the end, I can I'll pull up, Canvas and find it for you. Okay, so again, the carbs are polyols. They can do reactions involving alcohols. One of them is a unit 3 reaction called an ester with phosphoric acid. They are ubiquitous in biochemistry, that phosphate group. They're all over the place. Adenosine triphosphate, adenosine diphosphate. They're an energy molecule. They're used all over the place. So point on this slide is the carb is being used as an alcohol. Okay, so you can take any alcohol with a hemiacetal and it'll form a full-blown acetal. So with this reaction here, we have glucose, alpha glucose, because the OH is going down, anomeric carbon and carbon number 1. Plus an alcohol. In this case, we're not using a carb as an alcohol, we're just using, this is methanol. So it can also form a acetal from a hemiacetal, and that's what we have here. So we have OCO. So we're starting with a hemiacetal, OCO, and we have an H here on the anomeric carbon in OH's presence. That's a hemiacetal. We throw in a alcohol, in this case here, another glucose. We're going to use carbon number 4's OH group as the alcohol. And now we have a full-blown acetal, OCO, yes. H present, yes. OH present, no. So the OH determines whether it's hemi or not. Okay, so we have a linkage that attaches the two glucoses together. We have to name the linkage. Okay, so this is starting off with a beta over here. That means the OH group is up. So this O connecting here is going up. So to name the linkage, it's a beta 1, because that's the anomeric carbon that can go up or down. And it's attaching to carbon number 4 on the adjacent glucose. So that is a beta 1,4 glycosylic linkage. That's something else that's going to be on that questions about a specific carbohydrate. What's the linkage? So let's look at a linkage that goes down. Okay, so this is going to be alpha glucose. And we're going to put that together with another glucose. Let's make this one a beta glucose. Okay, so this one here, that's the anomeric carbon. And we have OCO. And we have a H present. And we have OH present. So that means that is a hemiacetal. Okay. On this side over here, on the right-hand side glucose, we've got an OCO. We have an H. And we have OH. So we have a hemiacetal on this one as well. However, when we put them together and they link up, the left-hand side hemiacetal is going to go to a full-blown acetal. The right-hand hemiacetal is not going to be changed, only the left one. So basically, this OH is going to bind there. So we end up with that going down. Because to start it off is the alpha. So this disaccharide has two moieties. Okay, so this is going to be an alpha one for glycosylic linkage. And that anomeric carbon determines whether it's alpha or beta. Okay, and this thing is called maltose, which is going to be one of your disaccharides you need to know. So there's two main types of reactions. When monosaccharides link up together, and whether it's oxidizable or not. If it's oxidizable, then you need to be in an environment where something can be reduced, like copper 2 plus, Ag plus, etc. So those two reactions are very, very important for this subunit. Okay.
For the next step, the pathway that we had. Like that. Paper that was given for the top.
I mean, the flow chart?
Yeah.
Yes. Every test you're going to get a flow chart. That's really helpful. To say the least, right? And I don't expect you to memorize that. I expect you to be able to use it. Because I don't like memorizing stuff either. In certain structures, you got to memorize. But that's just basic. Unless you have it on your little card really small. Okay, any questions about this reaction? Okay, you're fixing with your hair, not your hand, right? All right. Your ribose. This is a pentose, 5-carbon sugar. It's very important. It's used in RNA DNA. That's what links the subunits in that polymer together. It's ribose. With DNA, one of the OHs is gone and carbon number 2. That's why they call it deoxyribose. And if the OH is there, it's called ribose. And it's also furanose ring because it's 5-membered heterocyclic. Okay, so I'm going to go through all the ones you need to know. A lot of times when they have glucose present, to cover up the fact that everyone knows glucose is a sugar, they'll say dextrose. But it's an older name, still used a lot in the food industry, though. I see it on food labels a lot, still being used. Nowhere else, though. Mostly the food industry. It's used as a sweetener, but they use fructose much more now because fructose is a lot sweeter than glucose. Okay, so this happened to be the beta version because the OH is going up. Anomeric carbon and carbon number 1. If it was going down, it would be the alpha version. Okay, this has a heavy acetal. It has an H present and an OH. So that's a hemi. So that means this is a reducing sugar. Okay, a closely related sugar is called galactose. And the only difference is carbon number 4 goes up rather than down. It's down on glucose. Up on galactose. It's the only difference. Now, because it's a hemiacetal right here, so we have an OCO, so we have an anomeric carbon, we have an H present and an OH present, so it's a hemiacetal. So this is a reducing sugar. It's a really important sugar in your body. It's used in neurological pathways quite a bit. It's also a component of lactose. Now, fructose is a ketohexose. Hexose meaning it's 6 carbons. Keto means when it opens up to a ketone. It's almost twice as sweet as glucose. And these are the names used to hide the fact it's fructose. And in 1977, they invented a way to convert corn syrup to high fructose corn syrup. So corn syrup is not sweet. Only high fructose corn syrup is sweet. So who in here cooks? Don't everyone raise your hand now. I get confused. Karo, K-A-R-O, corn syrup is not sweet at all. It's used as a thickener. High fructose corn syrup is extremely sweet. And they're on the same shelf right next to one another. So Karo makes a pure corn syrup and a converted corn syrup. So if you're looking for a super sweet corn syrup, make sure you get the right one, because one won't be sweet at all. Okay, so fructose is alpha and beta also, and it has to do with this on carbon number 2, which is the anomeric carbon. If it goes down, it's alpha. If it goes up, let me draw it with in the beta condition. So this would be beta fructose. So those are the 3 monosaccharides you need to know: glucose, galactose, fructose. Particularly glucose. And I would recommend learning that one first, because galactose is really easy if you already know glucose. It's carbon number 4 is flipped the other way. Fructose, you need to it's kind of a different looking molecule. So that's another one you have to just know. But those 3 are the main hexoses in this subunit you need to know. Well, you need to know the structure when you do the reaction. All right. We can link, if it's a hemiacetal, we can link it to any of the carbs. Any of them. As long as one of them is a hemiacetal. And usually you put that one on the left. So it's hemi. Now this happens to be 2 hemis, 2 glucoses. And what happens is I'm going to get a linkage in the middle. That is an alpha linkage because you started off with an alpha glucose. So it's going to be an alpha. And I don't draw it like this. I like to do it like this because it's obvious that carbon number 1 can be up or down. Carbon number 4 has to be down. No exceptions, because if it's up, it's not glucose. So you don't have to say it's up or down. Now we're going to get to sucrose in a minute. Now sucrose is going to attach with 2 anomeric carbons. So then you have to determine what the linkage is. Alpha beta in one and alpha beta in the other one. Okay, so maltose, two glucoses together. So if you already know glucose, it's maltose is easy. Just got to remember the linkage between the two glucoses is alpha 1,4. So the thing about disaccharides, they can also be reducing sugars because the right-hand one can open and close. When it opens up, it exposes the aldehyde. When it closed, it's a hemiacetal. The one on the left, though, is now no longer a hemiacetal, but a full-blown acetal. That cannot open up. That stays cyclic. So if we analyze this, now there's two OCOs with a disaccharide. The one on the left, one on the right. So let's do the one on the left first. Okay, we have an OCO right there. And we have an H. And we do not have an OH. So that means that is an acetal. We have another OCO over here. It has an H and an OH. So this is an acetal. This is a hemiacetal. So the hemiacetal can open up, expose to the aldehyde. So it is a reducing sugar. Three dots means therefore. Top, top, top. Lactose. By the way, when you name this maltose, you have to say whether it's alpha or beta. Because the OH goes up, it's going to be beta maltose. Now, if you don't say whether it's alpha or beta, you're going to get dinged because it's not the correct name. Okay. So lactose has a glucose in it as well, and galactose. Galactose is always on the left. And this, by the way, is going to be alpha lactose because that OH is going down. Okay, so let's analyze this guy. So we've got 2OC, two OCOs. And we have, there's an H here and an H here. So we have H and no OH. So that means this is a acetal. This OCO, H is present and OH is present. So this is a hemi acetal. So the hemiacetal can be alpha or beta, depending on the direction of the OH. So whenever you name this, you're gonna have to name it alpha lactose. Linkage. Okay, because the OH group on the galactose is going up, it's going to be a beta linkage. The carbon is carbon number 1, anomeric carbon. And we're attaching to carbon 4 on the glucose. So the linkage is beta 1, 4. Now sucrose really looks different. And that's because sucrose is being attached at both the anomeric carbons. All the other disaccharides attach at one anomeric carbon and another carbon somewhere. Sucrose is different in that regard. Now, sucrose is really an important molecule. It's used in a lot of prebiotics. It's used a lot in oligosaccharides as a base unit. So it's used a lot. The important thing is if you're eating granulated sugar, which is sucrose, as soon as it hits your mouth, there's an enzyme called fructase that converts, sucrase, which converts your sucrose into glucose and fructose. So within seconds inside your mouth, that sucrase will convert that into a fructose. So normally you don't get fructose directly, you get it via sucrose. Okay, so let's clear all this up here. Now let's analyze these two anomeric carbons. We've got this one here, OCO. And notice the glucose is alpha, of the OH is going down. Okay, so let's so no OH. That means it's not a hemi. So this is going to be a full acetal. Okay. The other side where it's linking up to is another anomeric carbon. Remember, anomeric carbons are always on the right. So we've got the OH down here is going up. So is there an H on carbon number 2? Well, carbon number 2, remember carbon has 4 bonds. 1, 2, 3, 4. So no H. Okay. And then we have a and no OH. So this is going to be a ketal. Because the H isn't there. Okay, so is this a reducing sugar? Is hemiacetal present? No. So it's not a reducing sugar. Okay, frequently,
To determine alpha and beta, what to look for.
find the asymmetric or the, yeah, not the asymmetric, the, and then anomeric carbon. And the OH attached to it, is it up or down?
Up.
Up, it's beta, down, alpha. Okay, so, in honey, the sugar is not sucrose. The sugar in honey is glucose and fructose, separate, equal amounts of each. So honey is a sweetener also. It's just not the same as sucrose. Okay, so this is not a reducing sugar. Now, the linkage. What is the linkage? Well, we're starting off because the OH goes down on the top glucose. That means it is a alpha 1. And we're attaching to a beta as it's going, that OH has to go up to attach to the one coming down. And it is on carbon number 2. So it's an alpha 1 beta 2 glycosylic linkage. And again, no hemiacetal, not a reducing sugar. Okay. So those are the 3 disaccharides. Maltose, lactose, and sucrose. Now, an illegal saccharide has from 3 to 10 subunits. It's a more complex carbohydrate. Now, this one is extremely important because it's frequently given to babies in a formula or through the breast milk when they're feeding. And it's a prebiotic for the baby's microbiome. So the baby doesn't digest it. The bacteria in the baby's gut digests it. And if it's not there, it's got real issues, health issues. Okay, so what we have now, here, let's. Okay, so you're gonna need to know 2 illegal saccharides, raffinose and stachanose. Raffinose is the easiest one. So you take sucrose and add galactose. And where you add it is on carbon number 6 of the glucose. And that linkage is an alpha 1,6. Okay, and we still have the linkages and the sucrose down here as the alpha 1 beta 2 linkage. Okay, so is it reducing sugar? Well, are there any hemiacetals present? Well, we already showed that sucrose has none. Let's analyze the top linkage. This one here, OCO. So we've got OCO, H. There is an H there, but no OH. So that is an acetal, not a hemi. So this is not a reducing sugar. Now, you need to be able to do what I'm doing here for the test. I'm going to ask you all this stuff. For each of the units, you have to know. So it's not a reducing sugar, already shown that. Major carbohydrate in breast milk. Okay, stachanose and raffinose are very closely related. You add another galactose on top of raffinose, you got stachanose. Same linkages, alpha 1,6, alpha 1,6, and then the alpha 1, beta 2. So none of these are hemiacetals. So it's not a reducing sugar. And as I was telling you on Monday or Wednesday last week, the stachanose is on dry beans. So if you cook the dry beans, you just dump them in to a crock pot or something like that without rinsing them first, you get stachanose. Stachanose gives you gas. Bacteria love to digest stachanose into methane and carbon dioxide. So to get around that, you let your beans soak overnight and dump the water. A lot of people say you're dumping flavor. But you're also dumping something that'll create gas. Okay, if you've heard of Vino, Vino prevents gas from forming. That's because it takes apart the stachanose. So it's no longer stachanose. It converts it to sugar and a couple of galactoses. And there's one more prebiotic that is not use sucrose. And this is a pretty common additive. But it starts off with fructoses as the base and with the glucose on top rather than galactose. No hemiacetals present, so it's not a reducing sugar. And you'll frequently see it as a component of, and it's called inulin. And it's frequently used as a non-active component. You know, you have active components, non-active on your, and usually the inactive ones are binders. And that's what this is used for. Okay, so you have 3 sugars available in these test tubes: maltose, sucrose, lactose. we're going to dump in Benedict solution to all three. And again, remember with Benedict solution, if the color changes from blue to kind of a brickish, rusty color, it's a reducing sugar. If it stays the same, it's not a reducing sugar. So, maltose changes color. Sucrose, no reaction. Lactose changes color. So that means sucrose, according to this test, is not a reducing sugar, where maltose and lactose is. So these are the three disaccharides you need to know. You need to know their linkage, you need to know the whether they're reducing sugar or reducing reaction sugar or not, and why. And then we're going to get to polysaccharides. Polysaccharides are typically things like starch, cellulose, glycogen. Those are the three polysaccharides. Okay, so starch is simply a bunch of glucoses together with an alpha 1,4 linkage, except for the one on the far right. The one on the far right, now remember, it could be up to like 2,000 units, 2,000 glucoses together. But the one on the far right, on the end, the terminal end, is a hemiacetal. So starch is a weak, very weak reducing sugar because the terminal glucose is a hemiacetal. All the others are full-blown acetals. The name of this is amylose. Amylase is the enzyme associated with digesting amylose. Now, there's another form of starch-like that's branched. Now, starch, amylose, is not branched. Amylpectin is branched. And it's branched at carbon number 6. So it would be an alpha 1, 6 linkage. These are alpha 1, 4 linkages. So amylose, amylpectin are the two common polysaccharides that we can digest. Glycogen is the only starch mammals create. It's just like amylpectin, except it's more branched. Now, the last one is cellulose. Cellulose is the same as starch, only has a different linkage. It's got a beta 1,4 linkage rather than an alpha 1,4 linkage. And for the same reason, starch is a weak reducing sugar, same as said for cellulose. Now, we in our stomach cannot digest cellulose. It's a wonderful prebiotic, though, because bacteria do it fine. So it's frequently used as a prebiotic. Prebiotic, yeah. Okay. What? No more slides. Okay. I'm gonna end this now, and I'm gonna finish giving out the tests. And on Monday, I wanna go over lots of examples. Lots of examples. Because this unit is much more complex than unit one. And you need lots of practice. Naming, reactions, linkages, there's a lot to it.